All right, hi guys. Today we're going to have a science and physics lesson on what is heat. The response to my last video, which was that debate that I had with that fellow, there was a lot of positive response to my description of thermal energy and what heat is and what heat flow is. People seem to really like that. So I'm going to go into that in much more detail, and we're going to have an entire video here just on what is heat and what is thermal energy. And in doing so, we're going to see that we can actually totally disprove and debunk the field of climate science, let alone climate alarmism. Certainly climate alarmism is debunked by the definition of what heat is. And the entire field of climate science itself, too, is shown to be total junk science. So let us proceed. What is heat? It provides us the disproof of the climate change theory. It's going to be pretty interesting. So let's proceed. So let's first discuss different types of molecular or atomic movement. So here on the left, we have a sort of diagram of an atomic lattice that could be, say, the interior, the atomic scale, microscopic scale view of the interior of, say, a rock or a brick or something like that, okay? So these atoms are connected to each other with interatomic bonds, and they form a sort of lattice like this. Now this might be a crystal because the spacing here is all very nice and even, but in any case this is sort of a schematic, sort of a simple diagram of what the interior at the atomic scale of a rock or something looks like. Okay, so all these atoms are connected and held together by interatomic forces from sharing basically their electron shells with each other, and they hold each other in place. Okay, so let's consider first resonant vibration. So resonant vibration of these atoms would be, for example, when all of these atoms are vibrating back and forth, totally in unison, in resonance with each other. So they all move back and forth with the same amplitude, all together at the same time. So that would be resonant vibration. They're all moving back and forth at the same time together. So a good example of this is, for example, this wine glass here. So this wine glass is being pumped with a speaker, and you can see that this whole glass is vibrating back and forth. Now obviously here the scale of the vibration is obviously much greater than the scale of the interatomic bond distance, because obviously the atoms that make up this glass are very, very tiny compared to the scale, the amplitude of the vibration here. And so what happens is eventually the amplitude becomes so great that this lattice, this interatomic bond network, can simply no longer hold itself together. These atoms simply cannot any longer hold themselves to each other with the sharing of their electron shells in this with these interatomic bonds. And what happens is that they simply break, and that's when you get a shattering of the glass. Okay, so that's what happens there. Very neat. So mechanical movement would simply be all of these atoms all at once moving in the same direction. So if they're all moving in the same direction, that's simply mechanical movement. You're simply pushing the rock along, or you're pushing the brick, and they're all moving in one direction. In that case, there's no real damage done to this. They're not going to break apart because they're just being moved. So not a big deal, right? Another example that we are very interested in now and here is thermal vibration. So in thermal vibration, these atoms are all vibrating, but they're all vibrating effectively randomly with respect to each other. It's not truly random in the philosophical sense in that they have no cause and effect. Certainly, the vibration of any one of these atoms affects all of the atoms beside it, and there's cause and effect relationships with all of those movements going on. But it is so complicated that it is effectively random. So for example, this atom right here will be vibrating randomly around in a pattern like this, say, and as it's vibrating, its movement is being transferred to all of the atoms around it through the interatomic bond, and then they start vibrating as well, and they pick up that vibration, they're all sharing each other's vibration, and so it's an extremely complex sort of vibration, and it effectively becomes random and extremely complicated. And so that is basically internal thermal energy. And the amplitude of vibration here would be smaller than the interatomic bond distance, unlike that wine glass example. So the amplitude of these atoms' vibration is probably something like this. It's much smaller than the distance between between the atoms here. So that's thermal vibration. All atoms vibrate randomly. We could imagine this thing just looking like this. If this was at absolute zero temperature and these atoms were not moving, that'd be one thing. That'd be absolute zero temperature. These atoms would all be totally still. Now you could imagine grabbing one of these atoms and you're pulling it like this, and you're going to deform this interatomic grid, and then you let it go. And if you let it go, what's going to happen? It's going to want to snap back to its position, but in doing so, it picks up some momentum, and so it overshoots, and it'll start vibrating back and forth like that. If you were to do that, if you're able to grab one and then let it go, it'll snap back, it'll want to go into its normal resting position, but it'll actually start vibrating. But when it starts vibrating, all the atoms beside it are going to start picking up that vibration, because that movement is going to be translated through the interatomic bonds here. And then so you could imagine how the energy that you've put into this one by moving it with work done on it translates to everything else, and effectively you get heat transfer that way. So how to model atomic movement? Why would we want to? Well, why not? Of course, this is what we do in science. We like to understand things. So because, for example, we would like to know why a heated metal bar glows. So just think of that. For thousands of years, blacksmiths and metal workers have known that a metal bar will glow when you heat it. Imagine how mysterious that actually is. Does anyone actually even understand why that is? Think of how mysterious that would be to a person of thousands of years ago, that you find some metal and you heat it up and it glows. You know, in fact, it's still mysterious to the vast majority of the people on the population of the planet today. The vast majority of the population of the planet today would find just as much mystery in a metal bar glowing, if they would ever really think about it, as a person from 2,000 years ago. They still probably know just as little. You know what I mean? So why would a metal bar glow when heated? Now, why do you want to know things like that? Well, when we discover why nature works, it allows us to engineer nature. So it leads to engineering, to thermal and mechanical power, thermal engineering, mechanical engineering, power engineering, all sorts of different engineering that we can then use to direct nature in physics to do what we want it to do, which of course gives us the modern world. It allows us to cook things, make rockets and phones and light bulbs, and unfortunately a side effect is also it gives global corporate control over information. Oops, we kind of didn't want that one, did we? Nonetheless, understanding existence, even something as simple as why does a heated metal bar glow, it gives us power over existence once we understand why that is so, and what rules apply to such a phenomenon. So I mentioned in that previous video, in that debate that I had, something about about the atoms being modeled as a system of springs. So why did I say that? So I said that because we might like to know, for example, how much force is going to pull this atom back to its resting position if we were to pull on this atom and pull it to the side here. So here's its resting position. What happens if we were able to grab that atom and pull it to the side like this? How much force is going to exist or manifest to want to put that atom back in its place? So we simply model that with a constant times the displacement. So dx is the displacement, and this is the same thing as a spring equation. It's also a simple harmonic oscillator when you solve it in a differential equation, which I'll get to in just a second. So dx, that's the delta in x, or the displacement of the atom from its resting position. So you pull it to the side like this, and there's some constant, which we would have to figure out or solve from experiment. And the force is going to be k times the displacement. That's going to be the force that wants to put this atom back in place. So of course we have a whole system of that, and all of these atoms are vibrating. So you have an extremely complex system of a series of harmonic oscillators. Okay, so the solution to the harmonic oscillator looks like this. Oh, this is the differential equation for it, which you can solve, and the solution is actually simply a sine wave. So that would be for a single atom, but of course we have a whole series of atoms, and so you get sine waves actually built up on sine waves, because not only is this atom experiencing the force from this one beside it. It's also experiencing force from this one and this one and this one and to the side and up and down. And so there's a whole series of forces that are actually acting on this. And they add up in superposition simply because you have to add up all those forces. So you have a force in all these different vector directions and you add them up. And so basically you're adding up sine waves on each other. And so Fourier theory is very applicable to this, where you have a series of sine waves adding up on top of each other. In any case, that's what it would look like. That's the basic simple solution for a single atom with everything else fixed. As I said, of course, this whole thing is oscillating and vibrating, so it becomes quite complex. But we have solutions for dealing with that, and those solutions are the basis of thermodynamics, actually. So all atoms are connected with interatomic bonds. So movement in one atom induces movement in its neighbors. And of course, this is conduction, or what we also call diffusion, heat diffusion. So if these were all sitting still, as I was discussing earlier, and you were to grab one and pull it and then let it go, it'll start oscillating. But the nature of that oscillation, because this atom is connected to all the ones beside it with interatomic bonds through the electron shells, this one's vibration will be translated to all the other ones beside it, and so that energy will dissipate out and flow out, and that is your basic idea of conduction, and diffusion. Okay, so thermal oscillations quickly become randomized throughout the lattice just because it's extremely complex. It's effectively randomized. It's not truly random, as in meaning that they have no cause and effect, that one just randomly starts vibrating with no reason. Of course, there is a reason. The reason is because the forces are transferring, but you can imagine that once all those forces are translated throughout this lattice and all the different vectors of rotation, like of a vibration, these can obviously vibrate in 3D. It's effectively random just because it's extremely complicated. So what are the equations that describe this thermal energy and how it is gained? So is there equations that describe how thermal energy can be gained by a simple object like this, a simple lattice of atoms, which is what objects are made out of? And what is the collective distribution of frequencies of oscillation that leads to emission or glowing from the surface? We would like to know these things. Okay, so thermal energy, what is it and how to do it, how to get it? So how does thermal energy get into an object? So let's look at the equation for thermal energy here. So this is the du, that's the change in thermal energy of an object, is equal to the mass of the object times the thermal capacity of the object, which is its efficiency at holding energy, times the change in temperature. So this equation tells us that if you increase temperature, that means that an increase of energy must have occurred inside the object, the increase of free thermal energy. Likewise, if you increase the free thermal energy inside this object, that will mean that you have to have an increase in temperature. So if the energy goes up, the internal energy goes up, the temperature goes up. Or likewise, if you make the temperature go up by some means, then the internal energy goes up. So change in internal thermal energy directly proportional to change in temperature. So now let's look at the first law of thermodynamics. That tells us how we can actually achieve that. So if we want an increase of temperature from an increase in U, how do we do that? The first law of thermodynamics tells us how we do that. We do that by either having heat, which is Q, or work. So that's the first law of thermodynamics. So change in thermal energy is a result of heat and or work. You can have one or the other. So that's how you do it. So if we want an increase in temperature, we have to have an increase in du here, an increase in du. And if we want an increase in du, then we have to have either heat or work. Very nice, right? Very nice how that works together. And so what is Q? We really want to know what Q is because Q is heat. So Q, for example, would be this equation, which is the radiative heat flow equation for a plane parallel system. So heat can come from a hotter object, and the amount of heat we get is proportional to the difference between the hot object's temperature minus the cold object's temperature. So that's heat. Heat is the difference between the hot object's temperature and the cold object's temperature. So we'd consider that this is the cold object and we have some other hot object nearby, and this is how much heat we're going to get from it. And so that would be heat from thermal radiation, and that would warm up this object and raise its dT. So we have this, which is positive, coming from a hotter object. So because that's positive here, that's positive here, and that's positive here, and that makes a positive increase in temperature. Nice, right? So we note from this equation for heat that not all energy is heat, and that's very important to understand. Each of these terms, if you factor this sigma, this term here is a constant called the Stefan-Boltzmann constant, and that's the Greek sigma. If you multiply this in, you have sigma th to the fourth and sigma tc to the fourth. So those terms are themselves individually energy. Those individual terms are energy terms. They work out to joules. So those are energy. But heat is only the difference of those two terms. So not all energy is heat. Heat is only the difference in energies. That's very, very important. In fact, you will find in thermodynamics textbooks, and they will directly say this right at the beginning. They say the hardest thing for you to learn as a student that temperature, energy, and heat are different things, because when you simply come into university as a young student that doesn't know very much about the world, or even if you're a lay person, it seems probably intuitive for some reason that well, energy, temperature, and heat should sort of all be the same thing. They're not all the same thing at all. Heat is energy, but not all energy is heat, and that's what this equation shows. So these two terms are energy, but heat is only the difference between two energies. Okay, so that's very, very important to know that, or to recognize that. Okay, and then temperature, of course, is not energy. Temperature is basically the quality of energy. Okay, you have to multiply temperature by two other terms in order to convert it into an energy. So temperature is not energy either. Okay, very nice. So heat and work are the same thing. This is important to know, actually. Heat and work are the same thing. So that's that first law of thermodynamics equation, which we had previously. The change in internal thermal energy is equal to the heat gained plus the work gained. So for heat and work to exist on the same side of an equation with no constants multiplying them, and they're simply directly added together, well, philosophically and mathematically, that tells you that heat and work must actually be the same thing. They just perhaps work at different scales. They have the same units, of course, of joules. And so heat and work are actually the same thing. So change in internal thermal energy is a result of heat and or work. So it's important to note that heat and work are actually the same thing. When you're heating something, it's doing something similar to what work would be doing on the object. Okay, so we're going to understand this actually. So heat from thermal radiation does work. So this Q equation here, that's the equation for thermal heat, for radiative heat, for heat from radiation. And I've drawn here a series of waves, which could be considered electromagnetic energy coming in. So that's your radiation. And I've drawn here a series of wavelengths just to make it clear. So you would have from some source of thermal radiant energy, it would come with a spectrum, which we'll see in a second, but basically it's composed of various different wavelengths. So that's why I've shown the different wavelengths here. You have shorter wavelengths, medium and intermediate wavelengths, and long wavelengths. Okay, so those all make up the energy from some heat source. So it's energy of all different wavelengths, light of all different wavelengths, and they come in. So what work is this doing on the object? It's heat. We recognize that it's heat, and we recognize the equation for heat, but what exactly are they doing? Well, it's actually similar to the action of induced frictional heating. So imagine instead that this lattice here is the top layer surface of a piece of wood, and then you have another piece of wood that you bring in, and you're going to rub it on top of here very vigorously. Okay? So what's happening is by the action of the work you are doing with the energy of your arms, by rubbing those two sticks back and forth, that is work, for example, because you are putting the work in via movement. Work is usually something that is about movement. And in this case, of rubbing two sticks together to heat them up to make a fire, the movement is your arms rubbing those two sticks back and forth, or using a bow system in order to twist a wood or a stick in a little pit on another piece of wood in order to generate that friction. So what is friction? It's this lattice and you imagine another lattice on top of it moving back and forth. And so what's happening is that top layer of atoms on this one, this imaginary one, we're going to imagine rubbing back and forth on it. You're agitating those atoms manually. You are manually agitating them. Those atoms would be bumping and running over top of each other as you're pressing on them with pressure and with friction, and they're rubbing back and forth, and so they're simply agitating each other. They're basically like, you can think of, it's not too unreasonable to think of, they're a bunch of little balls connected by springs, and you're rubbing them together. And so what's the reaction of those balls on those springs? Well, they're going to start vibrating more vigorously on those springs because you're rubbing them and rubbing them and rubbing them together. And you can do that to such an extent that you can actually create a whole phase change in the physics of this object and start it on fire. And then that's a whole different realm of physics. Obviously, you stop rubbing at that point. So anyway, it's similar to the action of induced frictional heating, except in this frictional heating, except in this case, the radiation is doing the agitation. So this radiation comes down, and these atoms are all surrounded by electron shells, electron clouds. There's electrons that make up these interatomic bonds that are holding these atoms together. But electrons are very sensitive to light. Electrons pick up and see this light and are affected by this light, and the electrons will start being agitated at the exact frequencies at which they're being impinged. So the frequencies come in here of light, they hit the electrons because electrons are very sensitive to light. Electron, like it's the electromagnetism, right? The force of electromagnetism, light and electricity and electrons, they all interact together. It's all the same force, right? So these light waves, these energy waves of light come in and they agitate the heck out of the electrons surrounding these atoms. So what they're doing is they're agitating the interatomic bonds themselves. So as the interatomic bonds, which are made up of electrons, are agitated by this light coming in, that agitation transfers to the atoms on this top layer, and then those atoms deform and agitate their own interatomic bonds in all vectors, and so that energy thus gets transferred via conduction down through the surface to all the other atoms. So that's what's happening. So it's work on the atomic scale. That's what heat is. Heat is work on the atomic scale that you don't really see. I mean, work done by your arms rubbing those sticks together. You can see that happening, right? You can see it happening because it's, large scale, right? You're doing it with your arms. Yes, you can see that. With radiation, it's happening at a scale far too small for your eyes to see, but the same thing is happening. It's just happening on an atomic, molecular, microscopic scale. So these frequencies of light are coming in, they're agitating the heck out of the interatomic bonds, which are made up of electrons. Electrons are sensitive to light, will react to light, and because the interatomic bonds become agitated, that agitation transfers to, and they're agitated at exactly these wavelengths that are coming in. So if there's an electron right here making up part of this interatomic bond, it sees this wavelength, and it'll start doing that. It'll start vibrating exactly at the frequency of the photon that is coming in and is hitting it. And so now this interatomic bond starts deforming and being agitated, and so that agitation naturally transfers to the atom. This atom starts getting pulled back and forth because of the deformation of the interatomic bond here. And as that atom gets pulled back and forth, well, that movement transfers to all the atoms beside and above and below it, well, below it in this case, through those interatomic bonds. Okay, so isn't that neat? Work and heat are the same thing. Heat is basically work being done on an atomic scale that you simply can't macroscopically see. Okay, so heat does work. What work? What is heat? So what is it specifically? So what is happening specifically on a more in-depth level? We're going to have an even deeper look now at what is happening specifically to these atoms. So if these atoms were originally all at absolute zero, and this crystal lattice here was at absolute zero, then these atoms aren't moving. Now this light comes in, hits these electrons and atoms and agitates them, okay? So we see from the heat flow equation that it's something to do with the difference between a hot object sending its energy and the cold object's energy. So that's what heat is. Heat does work. What work? So heat increases the population of vibrational frequencies, and particularly at higher frequency. So originally, at absolute zero, there were no frequencies of oscillation in here whatsoever. The frequency was zero all across the board. There was no population of frequencies whatsoever. These energies come in, this energy comes in through electromagnetic radiation and start inducing oscillation, and all these atoms start picking up vibration. And so we want to know, for example, what is the population of frequency as a spectrum, or the population of wavelengths, where the wavelength would be related to the amplitude of the oscillation here. So heat specifically is the difference between sigma times the hot temperature and sigma times the cold temperature. So what this looks like as a plot here are these curves. So here we have the T2 curve, which is the hot curve, and the T1 curve, which is the cool curve, and that's exactly what these two terms represent. So each of these curves here is given by the Planck formula. This is called the Planck curve. So this formula is actually the original point, or the starting point of quantum mechanics, to solve this curve. So this curve is actually, or it describes the glow from a metal bar. That's what these curves represent. So eventually we were able to actually totally figure out a nice, relatively simple, although it's kind of complicated looking, but nonetheless a nice analytic formula for all of the energy that comes out from a heated bar. Isn't that amazing that you have a heated bar that's glowing, and you can actually describe all of the frequencies of energy coming out of that bar with a nice analytic equation like this? I mean, it's amazing that nature would follow something like that, right? So there was a lot of difficulty in figuring out what these curves were. Planck figured out that you need to apply quantization to the energy. That energy must be discrete rather than sort of continuous in analog. It's more like digital and discrete. And once you apply that to the equations, he was able to solve this. And before that, the equations weren't working out, and they weren't solving, and they weren't matching laboratory measurement. So anyway, that's the origin of quantum mechanics, was figuring out this curve, which is the curve of energy emission from a glowing metal bar. Isn't that neat? So heat specifically, getting back to that, heat specifically is the difference between the hot curve and the cool curve. The hot curve is always the bigger one, and it has a higher population of frequencies of energy across all frequencies. Plus it has the greatest concentration of population of energy at higher frequencies. Okay, that's what this black curve is, this Q curve is. So this Q curve is the heat. And we see that the warmer curve, the warmer object, has greater population of energy across all wavelengths, and it has the greatest population, or the greatest density of higher energies at higher frequencies, or at shorter wavelengths, which is higher frequencies. Okay? So, very neat. So you can't give what you don't have. So heat transfers from hot to cold only, and it can be thought of as a transfer of information. So what information? The information that heat is the additional population of activated frequencies. That's what heat is. Heat is this black curve, which I've denoted with Q, which is what we call heat in physics. Okay? It's this higher population of energy across all wavelengths, and particularly at higher frequencies or shorter wavelengths, okay? And that is information that can basically flow into the cool object, and by flowing into the cool object, that raises the cool object's temperature, because it's adding to the cool object what the cool object doesn't have, which is these higher frequencies and this higher population of activated agitation wavelengths or frequencies, okay? So obviously that can't go in reverse, because the cool object doesn't have what the hot object needs, okay? A colder body cannot give what a warmer body needs. It does not have it to give. So at Q equals 0, the hot object equals the cool object, and then heat flow is 0. So even though heat flow is 0, these terms are not 0. They're equal, but they're not 0. So each object is fully emitting energy, but the heat flow between them is zero, and that means that the temperature would actually be stable at that point. So why is this important for climate theory? Well, as we have seen before in my previous videos, the foundation of climate science begins with the premise that the sun does not create the Earth's climate, and we have actually seen them say this in the peer review process. They have actually stated and doubled down their position that the sun does not heat the Earth and does not create the Earth's climate. These are all foundational diagrams that are taken from various universities, and here even at the University of Chicago is a video lecture of the professor actually drawing a flat line on the board and writing in the expression for how powerful sunlight would need to be on a flat Earth, which makes sunlight unable to heat the Earth or create the climate. Okay? So, notwithstanding that this premise renders the entire climate alarmist theory ridiculous and defunct, because you're starting with flat Earth theory, and you're starting with saying that the sun can't heat the Earth. But because they start with flat Earth theory, where the sun cannot heat the Earth, they then develop this into a physics, into a new physics, where they say that the cooler atmosphere therefore creates the climate and warms the Earth by raising the temperature of the warmer surface. And they call this a greenhouse effect, even though it's not how an actual real greenhouse works at all. A real greenhouse works by stopping convection. What they have done here is they take this downward facing arrow, which they say is the emission from the cooler object, right here. So that would be the Tc to the power of fourth, the temperature of the cool object to the power of fourth. They've taken that downward facing arrow, which is the energy from the cooled object, and they say that it can increase temperature, that it increases the temperature of the surface to such a level that we then experience the climate that we do, because the sun, which they figure cannot heat the Earth or cannot create the climate, can't do it. And so now that we've gone over the equations, we can understand how ridiculous this is. Because remember, to increase temperature, we need an increase in thermal energy. To get an increase in thermal energy, you need either heat or work. Then the heat flow equation is this, but it shows that heat can only come from a hotter object, not from a cooler object. So basically, they're just simply having the colder atmosphere sending heat to make the warmer surface even warmer still. So it's just a silly sort of pseudoscience. It's basic pseudoscience is all they've done. All right, so I hope that was useful. I hope I got all the points across. Hope you enjoyed that. And please like, share, and subscribe. Everyone puts that at the end of their videos. I guess I've been doing it too. All right, take care, everybody. Bye-bye.